Hi all, this is Claudio from expertfea.com. It's my first time doing a live stream in ansys workbench. So with this small introduction, let me share my screen and we will start performing the FEA for stents, okay? So you will see my screen for a while. I'm in the beginning. Please have some patience. Firstly, let me show you my website. I think you might be familiar with it. Simulations, tutorials, and stress, let's say. We highlight biomechanics simulations. We compiled tutorials in FEA books. Other paid or free webinars, let's say, LS-Dyna FEA, live FEA support. If you somehow need our help, then we're here for you. So I opened the ansys workbench. Firstly, let's dive a little in what stents do. What are the application, let's say, all right? Here we can see very clearly that all the time when we have a plaque or an atheron or some calcification that let's say thickens the wall, the artery wall, let's say, the blood vessel wall, then the orifice or the diameter, which is helpful for the blood flow, it decreases so much that sometimes it can get blocked, and yeah, it's not a desired effect. This is where a stent comes into place. Here we have a catheter, the long wire, then a balloon which inflates the stent, and due to its shape, memory, alloy characteristics, at a certain temperature, the blood temperature, it stays in place after the balloon is removed. It stays dilated. This is what we will do today, all right? So we will import a stent from somewhere, maybe GrabCAD.com. Then we will model the artery with an let's say a plaque or an atheron here. So let's just do it, and we will certainly discuss more, and we will see what happens gradually. Okay, so at this moment, let's go on GrabCAD.com, and they change the page. All right, let's log in. Library, and here we are going to search for stent. We have lots of stent. Maybe at this moment you'll ask yourself, hey, Claudio, by the way, my name is Claudio. You'll ask yourself, hey, Claudio, why don't you design it or model it from scratch? There are some philosophy, there are some guidelines, some books, some advice that need to be taken into account. So, for example, stent guidelines or types. Let's see if they are here. No, they are not here. I have seen some books where they explain the principles of stent design. Here we can see some of those. We need This is diameter and length. We need a certain alloy. And the number of connectors. There are some small bridges between each portion, let's say. So a thing that needs to be taken into account, let me show you where, maybe here, okay? Yeah, of course. We somehow need to take into account the direction of enlargement or dilation, and we need to apply some bridges. Let's say maybe here. Come on, okay, let's hope here. Okay. So, for example, this is the dilation direction. It will dilate, it will enlarge, let's say, radially. This means we need to have such a curly shape in order to then be flattened, let's say, all right? So there is some philosophy, of course. There are guidelines that need to be taken into consideration. For example, this is a rhombus, okay? When it will dilate, this rhombus will enlarge and it will become like a square, for example. This is what needs to be taken into account. And a small bridge here. We don't need a big bridge or something, otherwise the stent will not dilate. More on what I have just told you, it will be seen here. For example, we have this design, okay? So having this hexagonal shape, we can somehow flatten it, enlarge it due to the dilation, all right? So should we work with this? Why not? Let's see if it works. Download. I already used it, so I liked it already. Let's go in SpaceClaim to look a little at the design. Let's see if we have something. This is something nice. This is not desirable because you have the ends, you have them very rigid, and according to me, it's not desirable. So inclined and curved. Look here, it dilates very much. Here, this curved and, let's say, sinusoidal shape accepts large deformation, let's say. So I will not use this because I think it is already used on the internet. So let me use a shape that is not available anywhere else. I think I need more recent SpaceClaim because this is 2022. Also, for example, because ansys workbench in general needs 3D models, you need to stay away from OBJ, STL, or IGS because they usually are shell bodies, or let's say empty, they do not hold water, while STEP or CSDoc, SpaceClaim document, they are clearly solid models. So, but we'll not use this because I've seen it used on YouTube, I think, and I don't want to somehow overlap or do the same things that others have done it. So I have told SpaceClaim to open, and we're going to open the solid part. I have downloaded a solid part. Solid part. It's here. For example, this one. Let's hope it works. No, it does not work due to a mismatch with the SolidWorks version. Then maybe let's appeal to another design. This is IGS, which means it needs to be healed. It needs to be solidified because it's a shell body. I used this in another simulation. I want to have a design that it's not so used, that everyone has used. Which one should it be? I have used also this. You know what? I think this, I haven't used it. The rhombus shape is pretty rigid according to my taste. Yeah, let's try it, why not? I will download this because it is a shell body and I will heal it in order to make it solid. Let's like it. All right, let's close the design space. We're going to work in static structure at this moment. So let's drag and drop static structure simulation. Right click, import geometry, browse, and we are going on desktop and we have Stent here. Back. Right click, edit geometry in SpaceClaim. Let's see what we have there. Once we will have the shell body, which we will need to solidify it. And second, we will model the blood vessel with the plaque. So, yes, I don't like it too much because there are different bodies, different colors, different bodies. Look here. They are solid. They are already solid. So we don't have shell bodies, I think. Let's try and maybe join them. So with right click, we select all of them and we go on design, combine. When I press combine, it will try and join, merge all the bodies. Let's see if it does this. Oh, yes, we accept. So you see, one body. It's nice. It's a little, I would say, wide. We click one edge, then we click another edge with control press, and we look a little maybe at the distance. Can we see the distance? We cannot see the distance. By the way, I don't know either if my the image is here. I think it's not interfering with what I'm doing. All right, I will remember that my image is on the lower right corner. So I select, as I told you, an edge and an edge on the same face. You see here, we go measure and measure. And we see a distance, okay, a width. It's 0.8. Yeah, I like it. It's around 1 millimeter. It's cute. Only I would say the length is kind of too small. So let's see, 20 millimeter. Instead of 20 millimeter, let's make it 40. Yeah, why not? This means we will choose the easiest way. We will make a mirror. Yeah, mirror is the easiest way. Mirror. We click a face here on the end, a small face, and we remember to, this is my likeness, I always like to uncheck this. I don't need mirror relationships. We need to merge mirror objects. So I selected this face. Let's see if something happens. Yes. So if I click this body, it will be mirrored. Okay. Click, and it's mirrored. Sincerely, so let's go with the easiest pattern we can make. Sketch mode. I selected the axis, yeah, or just click somewhere. With escape, you exit the command. With escape, click the axis and go on sketch mode. We are here. We select plane view, and we're going to somehow design the artery. Let's see for fun what is an average artery thickness. Average artery thickness. How does the average carotid 0.25, 0.25, blah, blah. You know what? Let's make it 0.5, the thickness. The thickness. This means we are going to make like an offset. I would like to offset the axis, okay? Let's see if it works. Does it work? I don't know if it works. No, it does not work. You know what? Let's do something like this. All right. I know that recently I can make such a dimension. We need the inner diameter. Average artery diameter. $10.25 something. Do we have? Mouse. What is this? All right. Yes. Mean coronary artery diameter. Let's say 2 millimeter in diameter. 2. All right. If we say 2, then we are too far away. Now what? This is for learning purposes. Let's make this maybe 8. Okay. You will see why 8. As we said before, let's make a thickness of 0.5. Here, offset curve. We have this curve. 0.5, I said, okay? 0.5 from the keyboard. Should we make it thicker? Let's make it thicker because we also have a very large diameter. Undo, and we have the same command. 1 millimeter. Okay. So at this moment, let's close this to have a closed contour, let's say. Then, because it's pretty random, let's create the data around the plaque. And because it's pretty random, we don't need to be very exact with what we do here. We end this here, right click, or escape, just escape, okay? Let's see for fun if we can move this point. Can I move it? Oh, yes, why not? To have like an uniform, let's say like a symmetry here. Where are we? Let's search for the trim, and we will trim here, here, and this, ladies and gentlemen, is our artery with atherome included. Okay, we'll make it one part. Let's see if we can revolve this. Hopefully. Does it work? Yes, it works. So we're going for pull. We're in pull command. We select revolve, select an axis to rotate about. We browse and the axis appears. We click the axis. Then I don't drag or something. It asks for an angle. And we'll write from the keyboard 360 degrees, enter. We need to select what to revolve, of course. So I selected the face and 360. All right. So this is the artery. I think we will need to make it a little thinner because I think it's kind of rigid now. If we somehow browse and click on the axis, we can go for the section view. Look here how it looks, okay? So, on my opinion, because the thickness is 0.1, I think it's too little. Let's ask. Average Stent thickness, diameter. We need to here. So there are parts, strut and bridges and whatever. 140 millimeter is 0.14. 140 micrometer, 0.14 millimeter. 0.14. Okay, let's see here, for example. Thickness 0. Oh my god. Strut thickness, micrometer 68. So 0.14 millimeter, okay. 0.1. Let's make it, yeah, 0.2, for example, okay, the thickness. Let's see how we can do this. Because we have 4.9, let's make this radius 4.8, just for fun. All right. Come on, it's just region. So I'm clicking and we have 0.2 thickness. Yeah, you know what, let's leave it like this. Why I want it thicker? Because the wall is pretty thick, let's say. Let's make the wall thinner, or 8.5 instead of 9. All right. And how can we do? What do we do? I would like somehow the thickness to be. So this face, I would like this face, the outer face, to be somehow in contact with the atherome, with the plaque. There are many ways to do this. The easiest way is like this. Maybe 5.2. Of course, in reality, and when you are working in your project, in your faculty, laboratory, or whatever, you need to have proper design, proper guidelines, everything. I'm just giving you, in principle, some directions. So you need to be more focused with correct dimensions and to have a reliable design, of course. Come on, regen, please. It's a simple regen. We're clicking on one of the small spheres. These systems, this coordinate system has some small spheres. Let's make it 5.3. Why? Because at least in static or transient, it needs very, very close contacts. So the gap value should be very, very small. Come on with the regen. Do we have a collision or not? I think it looks like we might have a collision. This means instead of 5.3, let's make it 5.28. So we're orienting about the x-axis, and we can verify if there is a collision with this tool, prepare interference. There are no interference bodies in the model. Should we believe it or not? Let's believe it. All right, now let's adjust the thickness because the thickness is too big. Before doing something else, let's save our project. This is called stream 1, okay? Stream 1, and we're working with 2026, January 01. Stent, stream 1, 2026, yes. This means also the geometry is saved. This is what we opened in SpaceClaim. So the thickness that we'd like is 0.28. It's kind of too big. All right, I am clicking on this face, design, pool, and we can say maybe 5.1. Let's see. Sincerely, I have no interest to make calculations at this moment, so let's just let's make a guesstimation, something from airplane. Yeah, no, not too exact, because we need to move to the finite element portion. It's the design and the modeling. While it is very important, it's not the purpose of our lessons. Operation failed, yeah, because we have, you see here, we have an interruption, and why not? Why not? All right. We click this face, sketch mode. We click plane view with control and the mouse, control mouse or shift mouse. Shift mouse, control mouse pressed. Yeah. Let's make something like this. And we write from the keyboard 10.1 from the keyboard. All right. Everything is done. Return to 3D mode. Click. It created a surface like a disk, and we will cut the stent with this disk. Okay. This means we're already in the pull command. We select here cut, and we're kind of dragging towards the other end. Okay. We can write some values, but no, let's just drag it towards the end. It takes a few seconds. All right, and look, it looks very nice. Here we should have around 0.23. Yeah, thickness, it's all right. Let's check in section if we are satisfied with what we have. We click the axis. We go on section mode. We click plane view, and we see. Yeah, that we are in almost close contact here. And yeah, it's nice. And we can check again the fact that there is no interference. Prepare, interference. There are no interfering bodies. What do we do now? Save. Click save. We should have had the stent a little bigger, or maybe decrease the length of the, yeah, let's decrease the length a little. Design, pull. My advice is always to click no merge. I would like the stent to be longer than the portion of the artery. This is, yeah, otherwise, when it will dilate, it will penetrate, it will collide, it will bloom inside the artery, and we don't need this. So this is what I would like. From my experience, I would like to have something like this, the stent to get out, to bloom. Something like this. Let's write 1.5. Undo. You know what? Something like this, yes. Shift mouse. All right. No merge is activated here. And we're going again. Let's see. Something like a symmetry. Yeah, it looks nice. Where we will have problems, maybe this edge, which is a sharp edge, will touch this face in an unwanted manner. We will see about this edge, okay? These edges, which are very sharp. We will see how they impact, because when it will dilate, this face will touch this edge and this edge besides the atrium, okay, or the plaque. All right, save. Let's go on with the FEA, and we will see what occurs there. So we're on the right way. Double-click model. We will continue with the FEA. Open. So this is the workbench window, and it will open the mechanical window in a few seconds. It takes some time because I closed SpaceClaim, and now it needs to reopen SpaceClaim. a good idea is to leave SpaceClaim open, let's say, in order not to take some time. Now it reopens SpaceClaim and it's transferring the 3D model. It says here mechanical window is locked when you touch a geometry. We have an error. We don't, maybe we don't care too much. I have a problem with my installation. In order to see the geometry correctly, okay, we go and the easiest thing is to click F7, which is like a zoom extent, okay? If you're going here, maybe you can also see the zoom extent somewhere. At this moment, I'm not interested where it is. I know about F7. All right. So let's take them in order. We have the geometry. A good practice is always to name the parts. This is the stent and this is the artery. All right. What we have as a next step, we need to define the materials, okay? Default is structural steel, of course. Let's somehow change it to something. Let's take it step by step. Yes. Let's look for titanium. Titanium alloy, preferably nonlinear. Nonlinear titanium, if we have. Ooh, we have it. Titanium alloy nonlinear. All right. And my preferred way to make a tissue, the artery wall, is my preferred way, the easiest way. Of course, not so exact or reliable, but is this one, right? Duplicate, rename. Rename, where is the rename? We don't care. We have F2, and we will say here artery. 1000 kilograms per cubic meter. Let's change here to megapascal, maybe, I don't know, maybe 0.1 megapascal. And the Poisson ratio for hyperelastic material should be close to 0.7. Sincerely, we do not need all of these. Let's delete them. Isotropic secant coil, we don't need this. This is the artery, okay? So it will kind of copy, it will mimic proper hyperelastic material, okay? Of course, in the future, in future simulation, and yes, you are going for hyperelastic materials. You can use such samples, and you will input from scientific articles. You will input your strain and stress, or your print rubber, biaxial, shear, volumetric. Feel free to do whatever you want. We can at this moment delete this, and we will work only with these two. Double click here, yes. Stent will change. We have question mark because I deleted the structure still. For stent, we'll select the titanium alloy nonlinear. And for artery, we're selecting, of course, artery. If you ask me why nonlinear, is because we will certainly exceed the yield stress, and we need proper stress values, not thousands of megapascals. If we had linear or simply titanium alloy, yeah, without nonlinear, then we would have obtained very large stresses which exceed the yield limit, and yeah, it's not realistic or reliable at all. Regarding the connections, we have only one contact, let's say. What I like to do, even though this model is very simple, I like to right-click, rename based on definition. It says bonded stent torque. Of course, the contact is frictionless. And at this moment, let's leave it like this. What I would like to do is to add also this face. Let's add this face. This means this face, the blue face, is on the target side. So this is contact red and target is blue. Yeah? Contact in ansys means the source side. A contact has two sides, the source and the target. And ansys, instead of source, it says contact. I would have prepared to be source, but it's just naming convention. It's not important. So let's click on the blue side. With Control pressed, we click this face, rotate with mouse, with middle mouse, click also this face with Control pressed, apply. And now you can see. Yes. So I want to keep things to minimum effort at this moment in order to be very easy for a beginner to do the simulation. I want to attract people to do easy things. Then in time, with expertise, we can complicate things, no problem. Just for fun, right-click, generate mesh. Let's see what happens. Yeah, pretty nice. I am always watching the node count, 37,000 nodes. Now, from experience, I don't recommend. In such deformation, I don't recommend hex. These are hex elements, let's say. I don't recommend them, so let's change the method. If you don't see, by the way, we can check them. Let me convince you. Selection information, and we will look for the element type. Right click, yeah, outside, right click, cursor mode, and we go for element, because I want you to see what type of element we have. Element, click, and we have selection information pressed. We click here, and it will say, this is a hex element, a hexahedron with 20 nodes, yes? With the mid-side nodes is a second order element. Look here, in the element order, what statics selects, by default selects the quadratic. Let me remind you what quadratic means. Quadratic means if we have such a shape, here is for an hexahedron. Quadratic means that we will, besides these nodes, besides the nodes at the intersection of the edges, quadratic means we have also mid-side nodes. Nodes in the middle of the element edge. All right, here. And it will allow somehow to have a second degree function. This is a, let's say, quadratic equation, okay? So we have this one, and an inflection point. Here on element order we also have linear. This means if we had linear, then we had, let's say, very quickly, I will make, we have only nodes at the intersection of the edges. Nothing in the midside. This means linear, this means we have a first order equation, which is something like this. Yeah, no inflection point in the middle, which is, let's say, a little stiffer. This is a little, it can become softer due to the inflection point. So if you want to count in a hexahedron, if you want to count the nodes at all the nodes, you will see that there are also mid-side nodes. But if you don't believe me, convince you even more. What I want to convince you, I want to convince you about the fact that in the middle of this edge there is a node. Yeah, also in the intersection of the edges. Let's prove it. Right click, cursor mode. We will put it. We will select node and look for the nodes. Look here, node at the intersection of the between edges, node at the intersection, node at the intersection, and look here in the middle. And if you have a hexahedron like this with all these nodes, then you will have 20 nodes, as it was mentioned before. Okay. Let me change mode again. Cursor mode. Yeah. Let me remind you. We had hex 20. We like to have tetrahedron elements because they are more flexible. Let's say. Okay. Oh my god, look at this. Look at the size of this. Oh, we should make it much finer. Let me prove to you that these are tetrahedron elements, all right? Because it's like a hexahedron, but somehow cut in two, okay? Click here, and we have tet 10. This means we have nodes also in the mid side and at the intersection of the edges. This is tet 10. Let me change cursor mode in order for you to see the nodes. So one node here, one node in the middle, and one node at the intersection. One node in the middle, one node at the intersection, and so on. All right. This is what program controls does in static and transient. Okay. Program control in explicit dynamics will select linear, but not here. Here it will select quadratic, which is like a second order, okay? Second order shape function for the element type. Let's go. We will uncheck selection information. I said that we need to change the method of this artery. Let's change it to tetrahedron. And look here. Also pay attention here at the nodes. All right. So what we have? We have everything is tetrahedron now, also here and here, but the mesh is very coarse. For explanation purposes and for the purpose of our live streaming, we will use coarse mesh because I would like to have very fast solving. I want to have results during the live stream, but not such coarse mesh because I think we will have problems. As a principle, as a rule of thumb, we need to have similar mesh density between this and this. Similar, not such coarseness is not preferable. Now, I would not say not allowed, but it's not preferable. Also, you have quality here, and you check for errors. But yes, you will do this when you are working for serious projects, when you are at work in your company. At this moment, let's not care too much about this, because we want fast results. Yes, so we have 15,000 nodes. Let's make a section view just for fun. We're clicking here on one of the axes. And let's make like a line. Section planes, new section plane. Let's draw like a line here, as vertically as we can. It's nothing is very exact. Look here, it's laughable or sad. I don't know. As, this mesh is pretty sad. Okay, so let's make it final. Sizing for the artery. Okay, right click. Do we have rename based on definition? We have rename based on definition. And size artery. How much? Normally I compare with this ruler, and I'm looking here, maybe 0.5, maybe let's try 0.5. And I'm watching the number of nodes. Okay, always watch the number of nodes in order not to increase very much your node count, thus extending too much your solving time. 330,000, as we would say in Chinese or French. This is kind of overkill. Let's make it 1. I'm trying also to make small jokes, but I don't know. I'm not sure of my rate of success. All right, so all right. So the step where many people they are going there, many were going towards the boundary condition application, and many people directly they go for pressure force in order to dilate the stent. You can do this, no problem, but it will slow, let's say, it will slow the convergence. My advice is to go for a displacement, let's say like a radial displacement, okay? That's for the purpose of the simulation. Let's try and test. What pressure should we use? Average pressure on stent, maybe? Pressure memory during before stick, and we need to try this one. I don't. I'm not sure about what this means. Contact pressure. Contact pressure range above 100, but this is pressure between stent and artery wall. I need the inner pressure that dilates the stent. Balloon artery. Ah, this is very nice. Balloon artery interactions during displacement. Max contact stress. All right. So So we kind of have something. Pressure versus stress, which is also pressure. Yeah, pretty interesting. Let's do something, I don't know. Systemic blood pressure after... Oh my god. Largest post dilation minimum MSC. Pressure percentage increase. MSC assessment biometrics increase. You know what? Let's use what we can. Yes. Let's start with one. Omega task. Let's watch the direction because it can be we can be fooled. Yeah, the direction is correct, is outside. If we change with minus, it will compress. It will collapse. Let's say. All right, this is the pressure. What do we want? We want somehow to hold either this or the artery. What do you want to hold? Let's hold everything, okay? So let's select these two faces and we will somehow restrict them in this plane, yeah? They will displace in this plane. Let's do the same with the stent, all right? Let's go for frictionless. And here we're going for cursor mode. We have box select, yeah? Something like this. Let's somehow select something like this, yeah? And also in this part on the right side, something like this. We only need the end faces. If you cannot have a box select, then click with Control pressed and select everything. Just do yeah, the best you can. Frictionless means these faces will remain in this plane. All right, so we kind of we have everything we need. At this moment, the only thing that is mandatory to have large deflection on. And let's save. I would like to see, let's say, live what occurs. This means solution information, deformation plot tracker, and stress plot tracker, because I'd like to see what happens during the solving. Right-click with Control pressed, switch to automatic mode in order to see live results, and also on solution at the end, deformation, stress, strain. Yes, we will add more, but not at this moment. Let's assign a number of cores. I don't know. Maybe just because we can. Let's put 50 and solve. All right, now let's go for the errors. My evaluation version gives some errors. Sometimes when trying to solve, clear generated data, yes, solve. So the solving sorted. We will have here like a log, all right? And look. So if we don't want to to read too much, we have what I like to use, force convergence. I'd like to watch. And here at force convergence, we need to have vertical green lines, which will mean that we have convergence. All right, we're on the perfectly right track. Look here, we have the first green line, we have the second green line, and yeah, it works. It works very nice. Let's see why it was so nice. Save, and we're looking at the results. So let's change from 40 frames per second. 40 frames per 2 seconds means 20 frames per second. Yeah, it's. I think it's not enough. The 1 megapascal, it's not enough. Look here, always check for the scale, true scale. Yes, we can exaggerate a little just to see if we're on track. And there is a like small rotation. All right, what we do as a good practice, because we like what we have obtained as a start, is we can leave it like this. What I do is I usually name it template and duplicate. Don't reuse the simulation, don't change, don't edit. If possible, always duplicate, because you might come back in the past to check past scenarios. So yeah, always go and duplicate. Save. What we will do, we will increase the pressure. So instead of 1, let's make it, I don't know, maybe 10. There was a rotation. Let's make here maybe 0.85. Let's also make the sizing for the stent. Yeah, Control B to select the body, Control B or cursor mode body. The default is 0 or is 2.3. Let's make it, I don't know, 0.5. We have right now 58,000 nodes. Let's see if it goes for, I don't know, 80,000 or 90,000. 116. Ah. Right click, rename based on definition. 0.7. Yes, and we can always look on the section view to see what we have. Yeah, it's pretty acceptable, let's say, pretty unique. These only 2 nodes here, cursor mode element, Having only two nodes here, two elements, it's not so so nice. Let's see. Let's hide here, hide the artery. I want to select this. Having two nodes here is not so nice. So obviously the mesh should be refined. Okay, I cannot select it very well because it's in a section view. So let's save at this moment and rerun the. So it started to work. So the default contact that we use and exists in ansys is it's working pretty nice at this moment. All right. We're pretty lucky. Save. Total deformation. And let's select here to scale. F7, remember F7? Right click, show all bodies. See how it dilates. I would say it's pretty strange. Why does it deform the... I was expecting for the stent to deform. Yeah, all right. So I think we need to restrain the artery more. Let's just do it. Suppress. We have similar simulation as the one before. This is why I didn't duplicate it, and I'm changing it. Even though I usually don't do this, I always duplicate. But yeah, we have. It's not so different from the one we had before. Cursor mode. Let's change to box select and or maybe single select. I said let's fix the ends of the artery. Do we have rename based on definition? No. Pressure, yeah, let's go for 50 megapascals because I think we have a pretty thick stent. This is the trial and error of finite element analysis, and yes, we need to test and repeat again and again and again and again. If possible, in the beginning, leave everything as default, as I let here. Yes. In the future, we will change now to time stepping. We will impose our values, let's say, for the time stepping, and yes, we will change more in future simulations. But at this moment, let's choose the easiest way. All right, other things to see if you want to pass the time. I usually look also at the time increment. And 0.2 time increment, it's ideal. It's very nice. We have here like a warning, contact status experienced, an abrupt change, check results carefully for possible contact separation. The workload is highly imbalanced for this distributed out solution due to the contact elements in this contact. This will negatively impact the scaling at higher core counts. You may select the offended pair via right mouse button on this warning in the messages window. We don't care. The source mesh cannot be correctly copied to the target surface. This might be because the surface is a closed surface with degenerate points. Splitting the surface might help. Yes, of course. So the red line is a non-convergence sign. So here we like the green lines. We like. This means we need to increase the pressure in a gradual manner, not directly as seen here. So, for example, when there is a bisection, the time increment decreases, yes? And you can see it here. We had 0.2, and now we have maybe 0.1, 0.05, 0.0226, okay? So, yeah, it struggles to converge. Let's see if it does it. Usually the maximum number of iterations is 26. And yeah, we're golden now. After a convergence of a substep, usually the time increment increases. Usually, and maybe it will go up, hopefully. So I'm watching this in real time, but yeah, when you will be watching this, you can skip and fast forward. So while it solves, let's. I found a good book for stents. I don't know where. LibGen. Don't be afraid to use LibGen and feel no shame, because also Meta or Facebook and Zuckerberg used LibGen to download terabytes of books, and they used these books to train their large language models for AI, for GPT purposes. So yeah, feel no shame in using such websites. Stents. I think I have it on my computer, but it's so. This is it's not arterial, it's not a cardiovascular stent, so we don't care about this at this moment. And this is not needed. I remember the book was Stent is not just a stent, if I remember. So always remember to use GPT, AI. Yes, Grok, Chat, you know all of this, and yeah, they have very good synopses or compilations, and for research they are very useful. And of course, use your head. Remember to always use your head. Top stents books to read. The baseball ball stents range. Oh. Handbook of coronary stents. Ooh, it looks nice. Let's see what's inside while also checking the simulation. It's not going too nice. You know what? Because it's not going too nice, let's just. We can interrupt, not stop, interrupt, and we will see what occurred until now. Can we see contents? And yeah, let's go on LibGen. Where is LibGen? What do you say? 2002. Download. Do I have a login? Let's see. What? Thanks for your support. Yes. Download. Where? Ah. Maybe I'm naive and download it. Where are we here? Hey. So now it looks nice. We restrained the ends, and yes, this is what we want. Let's solve this thing. I like what it does. This scenario I like to duplicate. Duplicate. Where are we? All right, handbook of corner stents. PDF. Oh, maybe this one. Maybe. 39. No, it's not the full book, but yeah, why not? Double click. Let's go again. Only the contents. Contents. Oh, it looks very nice. The Antares Starflex coronary stent system. Carla Di Mario. Balloon. Wait. Oh, yeah, it's nice. Strut thickness. Oh, very nice. Where were we? Here. Yeah, I said that there will be some convergence problems when we use pressure. Let's stick with pressure for this simulation, and instead of having 50, maybe let's make 3 steps here. And increase it gradually. 50 over 3 is how much? 50 over 3. 60. Let's make it 70. 17. 51, no? 15, 34, 51. Yes. Save. And solve. Let's go back to the handbook. Oh. Oh. Mountains. Seriously, can we find this PDF or not? Rotterdam, yes. Handbook of coronary, yes. Handbook of 255 kilobytes. Let's be serious. 11 pages. Yeah. Pretty nice. Nice article. Of the looking for the full text. Patient guide. So, about this simulation, does it work nice? It works very nice, I think. Force convergence, yes, we have a step converged. Let's look for the book. Let's look. Guide to cardiac catheterization. Oh my God. God help us all. Let's hope it will not be the case. The ballooning, the stent, yes. PDF download. Ooh. Let's see what happens. All right, so what is this? Pressure rinsing of coronary stent before implantation reduces inflammation and neo-intimal hyperplasia. Ooh. This is interesting. A phenomenological model of pulsatile blood pressure affected degradation of polylactic acid, PLA, vascular stent, medical imaging. And of course, they use only a portion of the stent because simulating the entire stent takes time and expertise and knowledge. Why not, no? So because we're here, let's look at some of my stents. The stents that I have used. And I'll not go for the easiest ones, let's go for the this. This is an easy stent. Easy, let's say easier simulation. Easy. Relatively speaking, easy. So we have a 3-folded balloon, yes? And the balloon inflates the stent. It's, yeah, it's very nice. So this one, let's see it. Oh, wow. I think this one is the one that I like the most regarding the balloon inflation. The balloon deployment. It was so much work, and in the end, it's superb. It's superb. Look, hexahedron. hexahedral mesh on the artery. Yeah, it worked. Hexahedral mesh also on the stent. Yes. Yeah, for easier and faster solving. Yes. Let's see. 1.4. We're on the right path. And yes, what I wanted to tell you, another source, let's say, for stents, if you somehow exhausted all the stents and you don't find any more challenges, even though it's hard to believe. Remember that you have also such websites like CG Trader, and you can go here for stent. Look here. Yes. Look for stent. CG Trader almost every time has, almost all the time has discounts, as you see here, discounts, sales, and everything. So, unfortunately, it mistakes at this moment with tent instead of stent. Let's refine it towards medicine and pharmacy. Cardiovascular stent. Does it make sense? Yes. So look here, more options, good prices, $3. Yeah, this is pretty, let's say, more expensive, let's say. But almost always you have them as, this is an exception. This is solid model. But sometimes you have them as STL or OBG or IGS, which they are bodies, yes? And this is an exception. This is solid part. This is very nice, okay? Let me prove to you, okay? This looks very nice. Click and STL. This is a shell body, yeah? You need to heal it and make it solid in order to properly use it in ansys. Okay, so CG Trader, it does not have too much parts, let's say. 1.4, we're aiming for 3, for let's say second 3. Another option is Turbo Squid. Let's look for stents. On this website, I observed that the prices are much bigger. This seems like a bargain to have 16 stents for only $9. Only. The problem is that if I remember correctly, yes, they are shells. These are shell bodies, they are not solids. It might be, sometimes it might be that you can ask for a conversion and maybe you'll get it, I don't know. Look here, so this is, let's say, nice, but yeah, it's not solid. So this is how the mesh looks like. But but they are not solid, and usually there are problems when converting them to solid. Very nice designs. Yeah, just take into account that you can have this. Or there is also this possibility of course, creating your own stent. Let me tell you what I want to say. Yes. So there are these, let's say, patterns or sketches. Not this one, okay? So if you somehow sketch these portions, then you can fold them axially or cylindrically. I have seen that easiest is to fold them in SolidWorks, because there is this command, bend command in SolidWorks, and this is a pretty complex command. And yes, this is, for example, if you have, I don't know if this one, no, let's see, maybe here. No, this is from the sheet metal, but knife bend, maybe deform. Yes, maybe deform. All right, let's see if I have SolidWorks installed. Yes. And I can explain to you pretty easy what I mean. So it seems to be a challenge here. Let's go and assign. So the first time step worked very nice. Let's go for the second and third with click pressed, with control pressed. Let's select the steps 2 and 3. Auto time stepping, I like time, carryover time step on. Minimum time step 0.01 and here 0.1. Save and solve. So we have right click, clear generated data. Yes, solve. Clear generated data. Yes, solve. Clear generated data. Yes, solve. Finally started solving. Where were we? Here. Let's see if I remember how to model in SolidWorks. Can we select a plane? Yes, and sketch. Do we have a... I would like a normal view. Do we have a normal view? Of course we have it here. So let's play with something like this. And here let's make some small squares. Can we pattern these? Can I pattern these? Mirror entities, linear sketch pattern, yes. Let's see. Direction 1. Instead of 10, let's make it 20. 25. 30. But I want to have the like bridger struts. 28. 26. All right. Instead of 2, can we make it, I don't know, maybe 6? Or maybe 5. All right. Then on direction 2, can we have a direction 2? Maybe not. Let's just copy down. Can I copy down? Let's see if I can copy down. If not, let's make a linear pattern. All right, instead of 10, can I make it 17? Or maybe 15? 16. All right. 4 times, or it's too much? 4 times is good. 4 times is good. All right. So have these, okay? Can I grab these and make it like this? Yes. How do I exit sketch? All right, exit sketch. Here, exit sketch. Can I maybe mesh modeling? What is this? Features. Extrude, okay. Oh, yes. 0.5. Ooh, yes. 0.5, all right. We have this, like a small window. $1.4. Let's see if we exceed 1.4, because in the past we had problems at 1.4. In the meantime, where are we? Here in SolidWorks. I wanted to show you that command. The command is maybe flex. Yes, I think it's flex. And this is how I propose you to create a stent by yourself. So this is the bend axis, which I would like, because I would like these ends to come together, to join themselves, let's say. What is this? Flex accuracy, I don't care. Instead, I care about this angle, I think. No? 90? Ooh. Yes. What about 360? Look. All right, so the command is flex, okay? So just imagine that you design your own pattern, yes? And you can join it, yes? You need to pay attention at the ends to have smaller bridges or less wide, all right? And you have this part, for example, yes? And you can always save it as, besides SolidWorks part, 3D models, step and parasolid. This is what you need, and usually what you need in ansys, or why not SolidWorks, whatever. So I gave you like an option on how to create your own Stent part using your own Stent design. Don't save. 1.4, again, problems. So what should I tell you about stents? Of course, if you're simulating stents, you are initiating and you know more than me on this topic. Yes, know about balloon deployment. So nice. If we only have the 3D models of this, it's so nice. So shell bodies. I will look for a second towards my smartphone to see if I received some notifications. Yes, I have something. Let me leave for 1 second. All right. So such a simulation, I think I made recently. It was here. Yes. And it looks pretty nice. This is the elongation or extension, traction of the stand. This is, again, this is torsion, rotation of the stand. You cannot grab it so well, so this is why it does not look so extraordinary. And the bending looks very nice. The bending, yeah, very nice, pretty nice, let's say. Where are we with the time increment? 1e minus 2. All right, let's let's maybe try and help it. Behavior asymmetric, formulation augmented Lagrange, normal stiffness factor 0.1, update stiffness each iteration, and yeah, let's leave it like this at this moment. We can also refine the mesh, but the solving will take more. If you're asking Claudio, why do you use 50 cores? This is the answer. Because it's possible. We have 64 physical and 128 logical, so yeah, we can go until 64, no problem. Ooh. Yeah. Ah, various designs. Yeah, very nice. Look here, how much. Very high stress, very high stress. I don't know if it's they used a linear, an elastically defined alloy, or maybe they used super elasticity. I don't know. Let's see here. Even the titanium alloy prototypes were produced with structures. On reviewing of printed prototypes based on material structures, we found that the Young's modulus magnitude was observed to be during its elastic response. Based on this experimental data, we decided to implement a simple linear elastic constitutive model. This is why we have such big variance. I think they did not allow plasticity. It's not elastoplastically defined. Otherwise, the values, I think, should have been a maximum 1000 megapascals from my experience. 1000 from my experience, yes. You can always look at my other simulations, and also remember to go on YouTube and search expert FEA stents, for example, stent. And you have here the stent that I have used and simulated. Look here, yes. Let's look a little, for example, at the stress values. Total deformation. Strain. Stress values, you see, maximum safe at 700. I think this, yeah, it's Nitinol super elastic. So yeah, but not 3000. Okay, 3000. It's too much. It's not. I would say it's not professional to have 3000 megapascals. Remember to search anything and everything. Yes, you want heart. What is this? Hemodynamic of the, okay. Stenting in the heart. Yeah, valve. Yeah, always look for whatever you want. Simulated by expert FEA. let's see here what we have. 0.1, it's very nice. 1.4 again. We meet again. Let's see if my changes in the contact details, if they helped or not. Live streaming, slow mode is on. All right. Stent 3D model. Let's see if we have something. Cardiovascular stent. Arterial stent. Sketch fab. Yegi. Yes, cardiovascular. This is what we have on GrabCAD, if I remember. Yeah. I think I know this from GrabCAD. But why not? Let's give it a go. A lot more, yes. Oh, this is very nice if it's available. This looks nice. Oh, this looks nice. Maybe this is nice. I don't know. So, does it work with the emotions? We will see. I don't know. We will see. What is this? Heart. Ooh. I like this. I don't know how useful is this, but I like it. Do we have a download? Of course not. Why do we have a download? I am here. Cannot download. Do we have a download 3D model? Should I download? In principle, yes. Download. This model is free. Of course, it's a shell. Let's download it because it's free. Why not? Do we have a download? No. It's a nice design. Do we have a download? We don't have a download, and I would have wanted to have a download. Do we have a download? Oh, I don't know how useful, but yes. We have download. By the way, here, yes, you can download such flat structures, and you can flex them. You can rotate them, as I showed you in SolidWorks. Flat arterial stent structures. Remember this, okay? On sketchfab.com, and you can make your own stents. Let's see. Do we have a download? No. Do we have a download? No. Oh my God, it looks so nice. Here. No download. This is overkill because stiffens the stent too much. Reject cookies, interact in 3D. Why should I interact in 3D? This is free3d.com and the price $149. So much for 3D. Free3d.com. Coronary stent model. What? Oh my god. This looks nice. This looks nice. All right, where are the stents? These valves look nice. This is too stiff. This is too stiff. Stent. So 1.46. It's we're on the right path. We are on the right path. No problem. You can forward and skip. No, it's easiest for you. What? It looks very nice. Oh my god. It looks very nice. It's very hard to find a good, reliable, hard 3D model. It's very hard to find a reliable, a useful 3D model for heart. Believe me. Oh, such a good valve. $30. It's 25. So they are separate parts. $30. Yeah. Not today. Oh my god, what is this? Pretty interesting and as a principle. Yeah, it's very well structured and it looks nice. And this is the valves look nice. It looks very nice. How much? $30. Interesting. All right, where are we? 1.49. Yeah, we're good. In order not to clutter all the points, the viewing points and the display points, we can choose here, I don't know, maybe 50 points, and yes. Oh, this guy presents very well made 3D models, very well made. Come on. Yes, they look anatomically correct. So much for 3D model. Where are we? Here, 1.49. Does it continue or not? Yeah. One point 5. So just take into account how much does it take to converge, okay? You know what? Let's presume at this moment that it converges with pressure. Let's presume. Let's interrupt it because I would like very quickly to show you the displacement option. Oh, but we are close to the end. Why not use it? Yeah. So at the moment 1.5, we have pressure around 25 megapascals. Yes, why not? Let's use 25. Let's remake this with 25 megapascals, then apply the displacement, the radial displacement, the radial dilation, because I want to show you how it should be applied. I will write here can be continued, maybe, and I will write that's too much pressure, because it is too much pressure. I would like to apply only 25 megapascals. (25/3). 20. Let's make it 24. So where were we here? 8, 24. All right. Do we keep all these settings? No. Let's make it program controlled. Save. And solve. Does it work? It does. Okay. So let me explain. Besides this scenario, yes, where we have outward pointing pressure, let's say, a dilation. My proposal is to have, instead of pressure, to have displacement. This means, let's make such a screenshot. This means we will do something like this. We'll have the a coordinate system that will be oriented like this. Let's say something like this. This is the axial. This is the outward pointing, let's say, radial. I will write here axial. And in parentheses, along gates. The artery, okay, let's say, or stent, if it were to be applied there. This is somehow radial, and it, in parentheses, I will say it dilates or expands radially, as it's supposed to. And there is another axis, tangential axis, something like this. It rotates the structure or whatever we use or we apply. What we will use, it will be this axis, because we need to dilate, okay? So if we have this orientation, yes, we'll use this axis. Let's remake the orientation. So we have, this is an axis, this is another axis, this is the radial axis, and this is the tangential axis. Yeah, and this one is the, I don't know, axial axis is kind of a mouthful. Yes, I want to show you how to apply the radial displacement, because we will use a cylindrical coordinate system. Look here, it goes very well. We are happy. And I think I didn't show you. Let's look at the live results, okay? Expand solution information, total deformation. Maybe it freezes for a few seconds. And yes. And maybe it's not enough. Also equivalent stress. Results seen while solving the simulation. Ooh, 1000 megapascals. Oops. The mesh is too coarse, nevertheless. And yeah, titanium alloy. This one is the most used. ultimate stress. Look here, so we can have around 1000, yes, and what we have here is around 1000, yes, so it's excusable, yes, it's normal, no problem. If it's heat treated, okay, even higher. Come on, finish it successfully. If these messages annoy you, click delete, no problem. Some emotions at the end. Yes. This is very useful, used in implants, prosthesis, and yeah, biomechanical parts, pharmacy, medical instruments, let's say, because it's usually it's biocompatible. Come on, end it. We want to go for the displacement. Yes, I think it will converge. Let's see what happens with the stream. This is the stream. Yes, very nice. Where are we? Stents. I would like you to see one of the most recent stent that I simulated, which is one used for intrauterine applications. This is the front of the uterus, and yes, it's very different. The philosophy of the simulation is very different compared to the one for cardiovascular stents, because the wall is much thicker and the dilation should be very high. There is no plaque, there is no atom, and yeah, it's a very, you'll see with the experience method, if needed, you'll see that it's a different philosophy of work. Got this great. We have nice results. Let's see here. So this is the end. 0, enter, right click, retrieve this result. Yes, it looks very nice. We can check the section view. Let's leave it like this for the moment, because I would like to show you the radial displacement, as I told you. Let's look. You know what? Let's duplicate. All right, this is finished. Duplicate. This simulation is made in explicit dynamics, and because we have used a very short application time, this is why you can see these waves, the shock waves. This is time agnostic, time dependent, let's say, while the static simulation is not time agnostic, is not time dependent, let's say. Setup. And here we will say radial displacement. It looks very nice. In order to in order to have a realistic time, we need to have better hardware, better computational resources. Here, so let's suppress the pressure. And we're going to dilate how much? So we would like, look here, the thickness, let's say, of the atherom is around 2 millimeters, yes? So let's dilate even more, maybe 2.5. Let's dilate with 2.5 per radius. We're not in the diameter, per radius, yes? 2.5. Let's remember this value, because here we are going for a coordinate system. It will ask for what reference, and we will select the outer face of the cylinder. Okay. Let's see it. We exit the section plane. All right. While we are here, we're going to change from Cartesian to cylindrical. And because we don't like the orientation of the y-axis, let's orient the z according to the x. The local z, let's make it collinear to the x-axis. This means we're going here, our z-axis we're making collinear to the global x-axis. Yes, look here. Yes, and we have what I told you. This is the, let's say, longitudinal axis, axial, as I said in the past. This is the radial axis that where it's important for us, and this is the tangential axis, which creates like a rotation, let's say. Okay. So now we're going here on static structural and select displacement. Displacement of what? We will say displacement of inner face of the stent. And for coordinate system, we will choose this coordinate system, which is simple. Coordinate system. We care at this moment, we care about, let's choose only the x-axis, okay? Let's make it tabular, free. And yes, I told you 2.5. Can we have, just for fun, I don't know, maybe, let's leave it, 3 meters. 2.5, this means 0.8. 2.4, something like this. Plus opposite dilation. All right, let's save. And let's see what will occur. Right-click, clear generated data, solve. Right-click, clear generated data, solve. Yes, it works. This method, from experience, using displacement instead of pressure, this method is faster solving, if I remember correctly. So let's see if it's like this. Yeah, it works nice. It works nicely. I would like to show you with different material properties. So we used the tissue, the artery tissue mechanical properties, and this is the plaque, the atheron, which has different mechanical properties. Remember in your simulation to do it like this with two different parts, okay? And the contact between them should be bonded, of course. We have used only a single part for faster solving, yes. It looks very nice because the stent is rounded, I think. It looks rounded here. Yes. Yes, here someone can see that it is rounded. Because when you have live edges, there is the so-called danger of cutting through the surfaces. This is why in ansys we kind of need to apply radiuses to smoothen the edges. Let's see here. It digs so deep that if we had a live edge, then it would have cut, let's say, or pierced through the plaque, through the contacting face or material. Look here, how hard it cuts deep. This is why we need to have smooth vertices or, let's say, fileted edges. Let's see, where are we? It looks promising. I wanted to see the stress for the stent. Where is the stress? Let's very nice. 400 megapascals. It's very nice, 400. But not 3000. Yes, look here. This is why we needed fileted edges into the stent, or outwards in the outer edges of the stent. So let's see what our colleagues have done with the stents. How to build the CAD model of stent. Oh, this should be interesting. If it's made from scratch, I'm interested. Yeah, let's. A little Chinese, I think. Yes. Let's see the rotation. How does he rotate? I'm interested because at this moment I don't know how to do it in SpaceClaim. He rotates it after this operation. What operation is this? This should be interesting. It's in the prepare command bar, I think. Prepare. And you need a shape. Okay. Let's see. Prepare. Wrap. Oh, how come I didn't know about wrap? All right. Let's wrap something. I don't know, 1 millimeter. Yes. Let's do also something. Can I? Let's pattern it. So grid offset, select a linear edge. This is one linear edge. Oh, yes. Options. Offset. Oh, this is nice. Yeah, let's just leave it like this. I like it. Pull. Something like this. And we want to wrap it, okay? So we're going here, sketch mode, view, and let's make a cylinder. Oh, should we? Does it matter? Does the diameter matter? Maybe. Let's. Oops. Let's move this circle if we can. Okay. Let's see if it matters. Prepare, wrap. Select a body to wrap around. This is a body. Select faces. Could not compute wrapping with current alignment data. Why? All right. Let's move this a little like this. All right. Maybe this is the problem. I want this shape to be smaller than the cylinder. I'm wondering if we need to correlate this length with the length, this circle length. I wonder. But yeah, let's see. Wrap, select the body, select face. Could not. Okay, let's select. No. So if we decrease the diameter, I think it will wrap, no? What does it occur here? No, 1.4. I have a deja vu. And it does not converge so fast as I said. As fast as I said, okay. Where were we? Wrap, select the body, select faces. Could not compute it. Let's make it, I don't know, closer. Maybe tangent. Something like this. Yeah, I think the diameter is too big, I think. Prepare, wrap, yes, no. All right, design, tool. Prepare, wrap, select the body, yes. I could not compute wrapping with current alignment data. Let's do something like this. The length is 40 and the length of this is, can we see the length? Measure 62. You cannot wrap 40 around 62. Let's make it much more. This means we need to have maybe 5. So the length is 40 and the length here is 31. Let's test. Prepare wrap. How is this guy doing it? And my Chinese is so poor. I cannot understand. Righty. He has some options here, and I didn't see those options in printers edges. What? Let's uncheck delete source. I don't want to know. was selecting the other way. Come on. I need to pay more attention next time. So, prepare wrap, and it says let's write to wrap around. This is the body to wrap around. And this is the face. It imprints. I don't want to imprint. All right. We will select geometry to wrap around the target. Yeah, someone I think is laughing. Someone I think is laughing about. What my trials. 1.75, it's promising. All right, where were we? Here. Select a body to wrap around. Select geometry to wrap around the target. This is the geometry. If I select this, select this point from which to start wrapping. All right. Does it matter? He selects the outer faces. These are the outer faces. It should work in principle. All right. 0.75. Come on. 51. Yes, there is hope. All right, where are we here? Grab. So select a point from which to start wrapping. Yeah, it's laughable. In SolidWorks is very easy. Yeah. Or maybe the problem is my pattern. Let's see. Yeah, it makes no sense. Can I ask Grok? ChatGPT. How can I wrap a thin body? How? All right, let's check the results. It's looking very nice. I think stress will be much higher than what we had before. Adjust to visible. Oh, yes. It's a little higher. Now I understand that 2.4 is, I would say, is too much. Let's make it 1.4. 1. Yes, 0.7, 1.4. It's nice. We know the direction. It's promising. Let's make it 1.4. I don't care about results. Do we leave 3 steps? Let's, yes. Yes. Where are we? Yes, no. This does not work in printed edges. Do we care in printed edges? We don't care. Let's do something like copy paste. Can we wrap this one? Yes, perfect. It does not work. What I wanted to show you. Okay, in order not to waste so much time, let me show you how to heal a stent. Shell stent, okay? So it was, we had a stent here, and we are downloading a stent. What stent should we download? This one? Maybe this one? STL, perfect. Download. Do we have another one? This one. Ah, it looks pretty nice. 30 minutes. Oh, this is very nice. All right, so let's go on SpaceClaim and import the STL that we just downloaded. All STL. We downloaded this one? This one, okay. So, oh, it looks nice. You can see facets, it's shell. It's not a solid, all right? We have 2 options. The option that I usually don't do and I don't use, it's right-click, convert to solid, merge faces. Why I don't use this, even though it kind of works, I'm left with these facets. And these facets will dictate the mesh. No problem, but it's not professional, let's say, okay? So undo. We go to facet. And here we try and fix, yes? We can click check facets, no problem. No geometry problems were found. Yes. What do we want now? We want to look for shrink wrap, for detect and fix sharp edges and vertices. Oh my God. Why? In the end, our purpose is this one. Tools, AutoScan. AutoScan will generate a 3D model or surface if it has a proper faceted body. Look here, AutoScan. It will not work because it has errors. Look here. It says could not generate cut surfaces. Yeah. Face is not planar, width unable to create blah blah blah. As I showed you, if we go to facets, it coincides with this problem, the sharp edges and vertices. So, what options do we have? This is a pretty straightforward and nice looking geometry. We have the option to click complete here in order to solve. Let's see what will occur. I have my doubts because there are 840 protrusions. It's very much. There are very many. We sincerely, if we had 100, 200, then it would have been fine, but these are kind of too many. Let's see. I don't know. Let's see. Look here. It's complicated. I will sneeze, I think. Okay, I stopped it. So we cannot solve these protrusions. We cannot solve this, but we have this option. Maybe it will work. I don't know. Let's see the thickness. 7 millimeters. Thickness 7 meters. The thickness is around 7 meters. We will scale it, nevertheless. What I want to find out is like a dimension, like a length, the length of an edge. 3 millimeters. So this is 3 millimeters. Because I would like to use this command, shrink wrap, which creates a faced body or shrink wrapped around the selected bodies. It will be like an offsetted part. But I need to find out the gap for the shrink wrap. You'll understand in a few seconds, if you don't already know it. Let's look here a little about the solving and convergence. It looks very nice. Where were we? Here. So my feeling is, let's use, because from here to here is 3 millimeters, let's use maybe 1 millimeter or 0.5. Let's see. Shrink wrap. Select a solid or faced body, then click complete tool guide to create shrink wrap. It will advise 12 millimeters, which is too coarse for me. I measured around 1 millimeter. Let's assign 1 millimeter. Keep original bodies, and in order to make it very precise, let's click preserve features. We can edit this, but I don't want to do it. Check. Let's see if it will retain the original shape. Let's see. If we assign a too small shrink wrap size, let's say, this operation can take very long time. So normally, if in let's say one minute, if this does not move in 1 minute or 2 minutes, then it will take too much time. And this is a sign that we'll need to increase this. Instead of 1, maybe 2 or 3. Because at this moment, it would be very fine, or the resolution would be too fine. So here, yes, very nice. We're on the right path. Let's click here. Because you cannot see it now, it's frozen. You can somehow, if you go to another window, you can sometimes hover over the SpaceClaim and maybe hope to see what will occur. If not, I think with Alt-Tab, look here, with Alt-Tab, you can see how it evolves, and it's not moving at all. This means it takes too much time. Usually, we need to somehow stop it. Let's try and stop it. Not stop sharing, stop the... Because we didn't do much, we can also exit the SpaceClaim, no problem. Let's open it again. So I want to show you how to solidify an STL or a shell body, to use it in ansys workbench for meshing and FEA. This simulation looks very nice. Where were we? Here. I said the STL. Facet shrink wrap. So instead of 12, let's try with 3. Keep original values, preserve features. All right. And if we have a look, yeah, this is fast. It's not so fine. It's not so accurate, and we will see if it retains the original shape and if it's useful for the auto skim command that it will follow. So how is the stream doing? Very, very, very nice. Lots of silence in this moment. All right. Yeah, the command usually makes SpaceClaim freeze. Look here, this is the shrink wrap. It looks we don't like these additions here, these small fillets, we don't like them. So this is the original, yeah. What we can do is maybe instead of 3, maybe make it 2, maybe. Undo, 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 undo. Because here I would like to change instead of 3 to make it 2. That those small fillets, let's say, those additional fillets would have increased the stiffness of the stent, in my opinion. This is why I didn't prefer them. But it works. Maybe it will take double the time, maybe around 3 minutes, and yeah, we will see. Where this are the second two? So much for the fast solving that I was promising. you need to take into account that this I've taken it from zero, from scratch. So yeah, usually simulation work taken from scratch, it takes days, you know. So yeah, it's we're on the right track. It's no problem. Yes, it's nice like this. What is the time increment? It's yeah, it's good. It works. I think here we'll have a converge substep here, maybe. Okay, maybe later. Oh yes. Oh yes, it looks much nicer. I don't know. Let's go for, we can check, usually there are no defects. When SpaceClaim makes a shrink wrap, usually it looks extremely nice. The density of the facets is yeah, professional. So if we click here, usually, yeah, I spoke too soon. What should we do? All right, let's go back instead of 2. Let's make again 3. And let's see if we still have the sharp edges, that big number of sharp edges. Let's see with the coarse resolution. Come on, Converge. Yes, we're in the green. So we have these. Let's see if we have. The problem is with these edges. What should we do? If I click auto fix, it does nothing. Okay. No holes, self intersection, no repair. All right. So yeah, for this case, I think we need to stick to convert to solid merge faces, or let's try something. Smooth. Does it work with smooth? I don't know. Let's see. Flatten peaks. Let's see. Come on. No? Nothing. Let's face it. Ah, it does. It makes them at each iteration, let's say. So, for example, oh, I don't like this. I don't like these webs or whatever they are. This was in the beginning, all right. I think we hit the maximum. All right, in principle we should have... Oh. Can we? No. Yeah, this is a pretty nice 3D model. By the facets, it's pretty nice. What we can do, a very nice trick. What we can do is something like this. Look here. A nice trick. Sketch. All right, sketch mode. Look here. We can try and find the center. How do we find the center? Let's draw some lines. So we will extract some points And we will unite now. I don't have exactly a diameter. No. I don't like these points. Let's project edges. This is an edge. This is an edge. This is an edge. This is an edge. I would like to extend these edges with the command create corner. For example, this to this. Perfect. So we located the center. This is the center. Let's create a point here. Okay. If I want, I can delete this. And here, I can create circles. One circle would be 240, for example. And another circle would be, I don't care this diameter, but I care about this diameter, which is 250. You'll understand now. So this will be a surface, and this will be a surface, and we will cut. You'll understand now. Return to 3D mode. So, I should have done this from the outer. I should have done this from another plane. Let's see if I can do it from another plane. If I paste here, it's not. But you know what? Let's. Oh, perfect. All right. So these, I do not care, but these I do care. So I will cut with this. So we now have a very smooth, very nice stent. And this, ladies and gentlemen, I will save and use. File save as. New sharp stent. I worked so much for it. So I had another stamp, if I remember correctly. So this I will not use it anymore. Peripheral artery disease. What is this? Ah, without any stent. Of course. Why would it be with any stent? Here instead of STL, let's go for all supported files, because I remember stunting instead of stent. Come on, dude. What are you doing here? Stent. I'll not try to open this because it's, I remember it's made in SolidWorks 2025. Let's go for this stent. For this stent. Ah, I have used it and yeah, it's nice. It's, yes. This is a mix, I think, between Spanish and English. Estante for heart. All right. Oops. These holes will pose some problems, I think, these holes, but it can be useful. All right, let's delete these holes. Selection, and I will select this face. Hopefully, so if I'm doing something like this, this is much work. Could this work? I don't know. Too much work. There will be complications in the future, so let's if I download it. What is Stent? Archive in archive, of course. This is promising. No, not anymore. We have this, and this is not promising. But maybe we can cut. Yes, we can cut something. All right, so right-click, separate all. Why do I have this this warning? The small triangle facets, check facets. Mesh has multiple pieces. Mesh is self-intersecting. Mesh is overlapping. Body contains none. All right, full of errors. This means I will do an autofix, even though it almost does nothing. It usually does nothing. Let's click again, check facets. No problems are found, in principle. All right, let's go for tools, auto skin. Only 4 errors. All right, facets, 9 protrusions. 5, 1. Let's do it manually. here, okay? So look how it's done. This face, all right. Delete. Delete. We have obtained 2 holes, all right? Holes, yes. Gradually. 1 and 1. Yes. So the auto skin should work. Tools auto skin. Mm-hmm. 2.4. Slowly but surely. Oh, it works. We have many patches in the auto skin, small surfaces, small portions. And if it does not work correctly, if we have many holes, it might mean, and we might need to shrink wrap the geometry that we have now. Yeah, I'm pleasantly surprised by the new stents. This thing, I think I didn't see it until now, or I didn't check it. What is this? This is very recent, but is it useful? It might be useful if we cut it. And let's download it as step. I didn't see this until now. New stents. And I thought I have seen all of them. I will download just for the challenge, but I know there is so much work. This one could be useful, but it's so much work. All right, where were we? 136. I don't want to wait. I don't want to wait. So let me STL up this. Or no? Let's go for the easiest. This step should be the easiest. Yes, if I cut it. I don't know. Let's create a plane. And rotate it. All right, so I will move this plane something like here, 15, 16. I will do the same here, but 32, 16. All right, why? Because I would like to split body once with this. And repeat, split body once with this. What happens if I mirror? I don't like this. This rotor, because it's too recent, Stent, simple Stent. I'm looking for symmetry for auto scan. Yeah, we're on the right path. The FEA, slowly but surely. All right, so no. So simple Stent can be deleted. and Stent 1. This seems more promising. Can be auto-skimmed. Let's see. So, as a result of auto-skinning, the facets disappear, so they are removed. They are joined into one face or big multiple faces. So, with the smooth geometry, without these small facets will not exist anymore. So here we are approaching the end, finally. Where are we? Here. Alt tab. We can look at the progression. This one takes longer, or let's look here. This is the auto skinning, not for this part, for the other, for the longer step. The windows are frozen for different geometries. So we're approaching the fourth hour mark, and yes, let's try and end successfully. What do we have here? They are overlapping, so one needs to be hidden. Escape. We will hide the facets. So this is apparent because it is a shell, is a surface body. This means we're going to repair with the repair command. Usually it's missing face. We have 3 missing faces. There are certain ways to do this. Let's firstly repair this one. 2 missing faces. And here, let's delete some faces. Yes. We will have irregular hole margins, let's say. Yes. Missing faces again. We have 2 missing faces. Gradually, we will solve this. We have a bulge, and if we solve this, we have, okay, this thing. It looks promising. Let me save it. Why it looks promising? Because I can cut. The error is here, okay? So I don't need this portion. These, I can cut them. I can use, for example, this portion. So let me firstly save it because new smooth Stent v1. Let's name it something else. I don't know. Superb smooth Stent v1. Okay, and here I can somehow cut it somewhere. Let's see where. Oh, it's a client. So this means I cannot cut it. I would delete it and use this as a v2. Maybe. Yeah, let's see. Always remember to right-click source, internalize all. Always, in order not to depend on any files in the other versions. Internalize all. Let's write here v2. What's happening here? Yeah, let's hide the previous faces. Oh my god. The result of the auto scaling is awful, to say the least. This means maybe, I don't know. Because it's so sharp, it's worth making it solid at this moment. And yes. Let's split it here. We delete this ring, and ladies and gentlemen, we maybe can mirror it. Maybe. Let's see. Select mirror plane here. Click. It's at. So we uncheck create mirror relationship. We don't care too much, all right? Is it good? It is. It's good. What do we have? What length we have? 150. Ooh, this is very nice. And the thickness is 1 millimeter. Oh, this is big. What I don't like are these things protruding. Let's shave them. This looks nice. Body. Yes. We like it. What we can do is make another shaving. Yes. Look here. So we will create a plane a little outside. Then we'll create those circles. We project this edge, we project this edge, then we do this corner operation. Yes, this is the center. We create a point here. We delete these items and we create our circles for the future shaving. 55.5. No, 56. All right, another one we don't care here, but we care here. How big? 56.8, for example. All right. We select this and this, and we go with cut back till the end. All right, this is a much smoother. Look, this looks like a stent. We need to work with the length and the thickness, but yeah, it's promising. Let's save it. We don't need all this. Right-click, source, internalize all. File, save as. Instead of superb smooth, how would I name it? You need to differentiate them somehow. Cute theme Stent V1. All right, and we had this thing. We need to work on those faces. This would mean that you know what? Let's make a shrink wrap of this instead of 4. Can I make it? We're going to find out an edge 0.5. Yes, shrink wrap. And why? Oh my god, it takes so much time. And we need to end the stream because it's too much time. Where were we here? Does it work? Yes. Shrink wrap. Open. Stent one? What is Stent one? This thing. But I worked on this. I can delete it. Delete. For this, which is very recent, I need to find. What? Of course. In order to be able to apply this looks extremely nice. In order to be able to apply the pressure, because we have so many different faces, we need to make the shaving that we did before for the other stents. How do I create a plane? I select one point from here, one point from here, and one point from here. With 3 points, I can create a plane. This plane, I can rotate it 90 degrees if I select it correctly. Then we move it outwards. All right. Sketch mode. Let's locate the diameter by projecting something. Look. So I don't know if you can see it, but there is a point here. Can I delete this? No, because the point disappears. This means I can make it construction. All right, so let's use this point and shave. How much? Let's give it a dimension. 29. 29 from the keyboard. Or maybe more. Why not? $29.5. All right. Another one. I don't care this one, but this I care. 32.5. Yes, 32.5. All righty. So we are here. We're going to cut until the end. Yes. But we obtained this error, which we don't really like. Can we make a mirror? Obtain this error, which we don't like. Let's make a plane there. Let's rotate the plane with 90. Yes. Perfect. If I am I in the middle? Do I care? Let's create 2 points. I'm projecting this curve and this curve, and I will select the middle. This is, oh, this is the middle, and this is the middle. Construction. Yeah, it was almost in the middle. Let's go and split the body with this and remove everything from the right side. Something like this. Let's mirror again. I think I had the opportunity to make the plane correctly. No, let's do it like this. Mirror. Uncheck create mirror, and let's see if it works. So we have this protrusion which we don't like. Maybe we didn't guess the it was. Out of curiosity, how much is this distance? This distance is 5.8, and this distance 5.8. Oh, this is nice. All right. No offense, but it's a very good looking stent. What we have here, planes, curves, we don't care. Oh, what is this? What is this? I observed that after splitting, it healed, the geometry healed, if you remember from 1 minute ago, or 2 minutes ago. It healed. So let's what is here? Shrink wrap. Do we care about the shrink wrap? It looks nice, but do we care? This is the question. Oh, it worsened here. It fused some of the branches. I would say that this Stent V2 is kind of doomed. Open. Delete. Instead of superb, let's make it smooth Stent. And here. I think the thickness is too big, too much. All right. We have many bodies. Let's fuse them together. Back. Combine. It kind of looks nice, but we have a problem. Yeah. Oh my God, it takes so long. All right, let's pause it a little. I am hitting undo, Control Z. Right click, detach. Let's do it gradually, okay? So, cut. Where are we here? It kind of looks nice. What? Need more. .5 is 1.25. All right, I would write that it can be continued. It worked. Uh, 150. $150. Yes, and this one. Cut 150. No, it gives an error. All right, no problem. This means we need to change the diameter. Maybe increase it a little. Cut 150. Yes. Very nice and superb. Right click, source internalize all. This name, let's make it solid. Say yes. Superb. Thin. Stent view. Super. All right, where are we here? Let's make it so faster. How do we make it so faster? Let's delete these. Here. Let's here make solver type direct. Maybe refine. Also here, do we need or not? Let's see what happens. Come on. How is this string going? Very, very, very nice. 100 and now save. Let's revert for the contacts. For the contact. Let's make it program controlled everything. Solve. All right, where are we here? This is saved. What are we doing here? Smooth standing on. Do we care about this? We don't care about this smoothing. No. So let's cut what we don't care. From here, I don't care. Can we create a plane? The geometry is so irregular because it will. I don't know. I don't know. Something like this. All right, so this plane, I will rotate it. Something like this. Then go. Here. 1.5. But it will be very hard to apply the pressure to extend. Maybe a balloon will help. No. Let's just let's delete this. Smooth stand V1. Smooth stand V1. All right, we had this thing, flat arterial, whatever. Let's delete it. Stenty. What is Stenty? More work for us. I close SpaceClaim. All right. I will check for a second the smartphone. It's nice. No new notifications. SpaceClaim. Let's open Stenty. What is Stenty? These ones for the flex wrap band, whatever. Flex wrap band. Here there are some problems here and here. All right, what is here? Oh my God, the angles, so awful. This seems kind of, this could be kind of acceptable. Right click, separate all, delete, delete. This could be something. Even though it's very irregular. Regularize. I wanted to get rid of these small triangles, and yeah, it's not possible. 88 protrusions due to the no, some sharp edges. If I hit protrusions, okay, why not? Let's solve them. We need to delete this face. We need to delete this face. We have a hole, and we healed the hole. This means we have one more protrusion to solve, this one. We delete these two faces, 1 and 1, hole, solve. no protrusions. This means we can easily go for 0.37. Yes, let's leave it. Again, we can easily go to AutoScan. And what will occur? There are some refinements, or I don't know how to tell, hotspots of facets, and yeah, let's see. What? It's the first time when I see this. Could not generate cut surface. See the surfaces. You know what? I can't shrink wrap it, I think. The length of this edge is 3. I can shrink wrap it with 1, maybe? Facets, shrink wrap, pack. 0.5, keep original bodies, preserve features. Let's see. So the stent is much work. All right, escape. We hide the original facets. Let's check for the 40 protrusions. All right, there are no protrusions. Tools, AutoScan. It might take a while. Or not. By the way, because we're here, remember to check the materials in Stents. Chromium, stainless steel, methanol, shape memory alloy, platinum, chromium, bioabsorbable. This is the latest thing because they kind of dissolve in the human body. Of course, all these materials impose different behavior. in FEA, also in reality. Type of polymer coating. DS is drug eluting system. Drugs stenosis. Yeah. Stainless steel cover chrome platinum titanium granules, local distance, drugs, rolling, paclitaxel, metallic engineering drugs, Zotaulimus, Eferolimus, metallic platform, cobalt, chromium, platinum, biosolvent stents, PLA, polylactic acid, polyepsilon caprolactone, polyglycolic acid, magnesium, iron, and iron alloys, zinc alloy. So each of these materials imposes different behavior, different advantages and different problems, of course. To reduce magnetic artifact generation during magnetic resonance images against that material properties. To extend balloons, balloon pressures, high radio opacity, attenuation coefficients, to reduce the clinical complication associated with blood clot formation inside the implanted stent. Yeah, bioresorbable scaffolds. PLA, polylactic acid, polymer salicylate. PTD, PC is polytyrosine, derived polycarbonate, semi-crystalline polylactic, and polylactic acid. Strut thickness, resorption. Yes. So you need to be aware of all these materials and use them with caution, with expertise. Where were we? Auto skin. Oh my god, so much time. Yeah, these two stents seem pretty different. Resistance. Yeah, nice. Compounds. So, guide to stent manufacturing, material selection, laser cutting, electrochemical polishing, cleaning and sterilization, inspection, quality control, packaging. And I think they are pretty expensive. From scan generate, basic undeformed stent, segment print, slice model, golden Cura, overmolded print, subtract cylinder. This is the flowchart describing the patient's stent manufacturing process. Printed current tracheal airway. The big stents, the large stents are for the trachea. For Stent, and calculate nozzle toolpath, finalize G-code, print, trachea, and Stent. Dual therapy Stent, latest type, contains a drug with active healing technology, has coat on both sides, bioresorbable vascular scaffold, rapid standard dissolvable type of scaffold sold over time, coated with drug release from polymer, reduces the chance of restenosis. Bioengineered stent, antibody-coated stent, does not contain a polymer or drug, speeds up the epithelialization of the artery, promoting natural healing. Drug-eluting stent, coated medications that help to prevent the growth of scar tissue in the artery lining, chances of blood clot, stent thrombosis. Bare metal stent, stainless steel without special coating, as arterial tissue grows around stent, holding it in place. Overgrowth of scar tissue, high risk of re-blockage. Yeah. Cardiac stents from research to clinical applications. So they make sense, these designs. Oh, yes. Esophageal stents. Oh my god. So we can have big stents. It depends where we insert them. You know what? Let's force another solving. Let's make it even faster solving because it takes too much time. How? 1.2. 1. Will it work? Let's see. And here, let's apply a little something we call stabilization. 0.1. Yes. Save. Solve. It works. So let's see the result of the auto skin. What is this? Oh my god. It's better that, but not perfect. Repair faces. Here we have multiple missing faces, and the order will not be correct, and it will be a disaster. Let's shrink wrap the shrink wrap. At this point, we're just playing. So I think I was kind of right, because the solving is much faster. But let's see if it converges. Yes. And we're approaching the end of this session. So we have this shrink wrap. Do we have problems? Yes. No problems. Auto scan. How does it work? Should I open Solidifying meanwhile? That's okay. Oh, my convergence. All right, where are we? SpaceClaim. Does not look nice. Let's hit solve, even though yeah. So much for the fast solving. All right. What do we do? achieve fast solving. We can use this thing called adjust to touch. Let's see if it helps. I refined a little the mesh, very little. So nothing here. I liked something. I think this thing is nice. Yes, I need less facets because I would like to flex to wrap this thing in SolidWorks. So facets. Yes. I got rid of the small triangles. Three millimeter. Just for fun, can I make a shrink wrap of 1 millimeter? Yes, but it looks worse. What about 0.3? How's the stream going? Very nice. Does it converge? Yes. Where were we? SpaceClaim here. Come on, converge. I don't like these spikes. I will remove. I will remove the stabilization. Still activate line search. Why not? Very detailed shrink wrap. Can I make an auto skin? After we solve these, yes. How much does it take? How long will it take to auto scan? We will see. What have we here? 0.4, and it looks much nicer. All right. Here is not so nice. Where are we? SpaceClaim. I think it takes too long. Yep. We need to face the fact that Stent is not so useful. Goodbye, SpaceClaim. 0.56, all right, it goes very nice. So, other stents. Ansys. I've seen this. It's decent, although it's a quarter symmetry. Other stents. Abacus, of course. Stream scale. Let's see. I know this guy. He does very nice stuff. I think this is not. What is this? CFD. Plague cholesterol instead of plaque, cholesterol plaque. Plague cholesterol. Come on, dudes. Oh my God, what is this? This is animation or... this is some CFD. So, SolidWorks associative interface for Abacus. What? God, the resolution is awful. It's nice work, but yeah. Yeah, this is a masterpiece. Absolute masterpiece. Quarter symmetry or less. Axial symmetry, yeah. Axial symmetry. Come on, dude, it's 0.56. All right, reaction time. Nice displacement, nice stress. Fatigue, because it's in static, okay. Yes, it's only simple stent. No artery, no balloon, no. But nice work. It's nice work. Where are we? 0.56. Oh my god. What is this? Awful resolution. Who uses 720p? It's a crashing and no fixation. It's solved. What are you doing? What? No. Ah. Yeah. Yeah. Mm-hmm. In the end, it looks nice. I like that he used the line body, the beam, the line body. This is nice. He used line body. Yeah, it's in the end, I like it. Mm-hmm. Oh my god! Oh my god! So it looks nice. It looks nice. Let's interrupt it here and let's close this live streaming. You have seen lots of methods to do the FEA. Then I got greedy in order, and I kind of tried to shorten the solving time. But you have seen lots of methods to solve this without any problem. You can also assign a contact tool, and here you can see the pressure, sliding distance, and penetration. So look. No friction stress because the contact is frictionless, of course, sliding distance, penetration. Absolutely. So that's all from my side. We'll meet you again in a few days for the next live streaming of the FEA and ansys workbench. Thank you for the patience and have a nice day. Thank you. Bye bye.